Chapter 6, Number 40. Two blocks are connected by a string as shown in the figure. The smooth inclined surface makes a given angle with the horizontal, and the block on the incline has a known mass, whereas the mass of the hanging block is also known but different. Find A, the direction, and B, the magnitude of the hanging block's acceleration. So we'll need to figure out what the tension is and how the two blocks move. To do this, I'm going to presume for the moment that it is not enough to hold up the block, and so that the block descends. That isn't irrelevant. We can just pick a direction and fix it later. So our first thing would be to draw some free body diagrams. And we do something like this block. I'm going to give them some names so I can talk about them. So this is block 1, and this is block 2. And like I said, I'm going to presume, without any real proof right now, that block 2 descends with some acceleration a. In so doing, the string connecting them, the rope connecting them, does not change. It stays the same length. Since it stays the same length, they are always the same distance apart, which means that for every centimeter that block 2 drops, block 1 must move up the incline, so that they must have the same acceleration. They must have the same velocity at every moment, which means they must have the same acceleration every moment. So that's a long-winded way of saying block 1 accelerates up the incline at the same rate that block 2 sinks. All right, let's start putting some forces in play on these bodies. So we always put in gravity. So block 2, I'm going to call it FG2, and block 1, FG1. I need to give them different names, FG1 and FG2, because they are different masses, and so they'll have different weights. If you use FG for both of them, you will get into trouble. All right, what else do we have? Well, for block 2, we have the string pulling up, which I'm going to call F sub T. It's tension. Walker likes to just use T, but I use FT instead to remind you that it's a force. And likewise, the string is attached to block 1, and it pulls it parallel to the incline, meaning parallel to that acceleration, which will turn out to be kind of convenient later on. But also, block 1 is in contact with the incline, and so that's going to give us something a little bit different, because we're going to have a normal force, and the normal force is going to be perpendicular to the incline. So something like that. We're used to the normal force being opposite to gravity, but since there's an incline, that's not actually going to be the case. It is, however, a smooth inclined surface, so we may assume the friction is 0, so there are no other forces coming down. Because of that, for block 1, it's going to prove, since block 1 accelerates along the incline, it proves convenient to take our tilted axes as before. That we have a y-axis and an x-axis. And in so doing, we're really going to end up changing FG. So let's reproduce this diagram a little bit cleaner, and we're going to say that we'll have an FT along the incline, and we'll have an FN perpendicular to the incline, but we'll also have an FGY, which is into the incline, and an FGX, which is down the incline. And that's coming, we're really saying we're going to break our FG into these two parts, FGX here and FGY here, and this angle is going to be the same as that angle. We'll call that theta, and therefore that will be theta. That geometry has been done a couple times in the lecture notes. It's done a couple times in the textbook. It's worth you convincing yourself that we can just move the angle over that way. All right, that lets us say that FGX is FG sine theta, and FGY is FG cos theta, and that comes from just defining sine theta and cosine theta using this triangle. You really should feel comfortable deriving that and not simply memorizing it, because it's obviously dependent on the geometry in the problem, and If you just memorize it, you know that at the worst possible moment, the geometry will betray you and stab you in the back, and then you'll have the wrong ones down. But it will certainly turn out to be that. So, from the diagram, we can get some expressions for our forces. We'll have 3 of them. We'll have the sum of the forces on one along the incline. We'll have the sum of the forces on one perpendicular incline, and we'll have the sum of the forces on 2, which we'll call just for 2, we'll say this is our axis. And it's actually perfectly fine to have different axes for different objects as long as we translate between them carefully, and we'll end up doing that. And so we see f1x is going to be, well, it has an ft on it, but it also has an fgx. And because fgx points opposite to our axis, it comes in with a minus sign. And then f1y has an fn and fgy, but again, fgy goes into the incline and our axis is off of the incline, so we get something like that. And then finally, we have here that ft pulls and fg2 pulls, but fg2 pulls downward, so we get that. And then we have, from Newton's second law, we have the sum of the forces in the x on one, and the sum of the forces on the y for 1, and the sum of the forces on 2 in the y. And we look here and we say, what are our values here? And we say, well, we have, this is obviously mass 1 times the acceleration along the incline, which is just a. And for object 1 moving off the incline, well, it doesn't. So its acceleration stays 0. And we multiply by m1, we still get 0. And then for f2y, we have the mass of 2 times the acceleration of 2, which is the a. But we have to remember that it's a downward. What this ends up meaning is that the weight, if I'm right, the weight will exceed the tension. And it's entirely possible I'll be wrong, in which case the acceleration will come out with a negative, and we'll interpret that as saying it moves the other way. So now we need to combine these. It's a bit of algebra I'm going to do on the next page. I'm also along the way going to use things like that each fg is that m times g, and I'm going to use the components over here from the geometry. So I'm going to put 2 things together at once, and hopefully it won't be too bad. Alright, so combining everybody up and using their components, we get the equations as shown here. We've now combined the free body diagram with Newton's laws. Our very first thing to look at is that our middle equation here is true, but turns out to be kind of useless because it connects things that have no other use in the problem. Specifically, it connects Fn to everybody else, and Fn doesn't appear anywhere else, so it doesn't give me any real help. What we want to do is find A, and we want to find it in terms of things we know, and most especially the thing we don't know, we want to have go away, and that's Ft. And there are many tricks for doing this. For instance, we can solve for Ft in terms of stuff and then eliminate. So I think I'll do that just to be different. You can also do things like subtract the second equation from the first equation. But I'm going to do it slightly the way I just said. I'm going to actually just combine, solve for Ft and combine them. So I end up with that Ft, according to the top equation, Ft is m1a plus m1g sine theta. And I also get that from the third equation that Ft is, and here we'll have m2g minus m2a. And if two things are equal to, right, this Ft is definitely equal to Ft, so then these two things have to be equal. So we end up with m1a plus m1g sine theta is equal to m2g minus m2a. And what I'd like to do is get the a's on one side, so I'll add m2a to both sides. And that means I want to get g on the other side by itself, so I'm going to subtract m1g sine theta from both sides. And that's going to yield for us m1a plus m2a on this side, and over here it's going to yield m2g minus m1g sine theta. I'm going to do just a tiny bit more math tricks. I'm going to factor out the acceleration on the left, and I'm going to factor out g on the right. So I end up with m1 plus m2 all times a is equal to m2 minus m1 sine theta all times g on the left. And so I can now combine, and I can say something like a is, and we're going to get something kind of weird. It's going to be a fraction where the top of the fraction is m2 minus m1 sine theta, and the bottom of the fraction is m1 plus m2, and then all of it is going to be times g, which is not surprising. It's sort of a factor of g, because g is what's causing everything to happen here. For our particular problem, then we get the following values. We have that the hanging block is 3.2 kilograms. So we have 3.2 kilograms minus 5.7 kilograms times sine of the angle, which was 35 degrees. And on the bottom we have 5.7 kilograms plus 3.2 kilograms. And I am definitely cheating here a little bit, but I know that the kilograms on the top and the kilograms on the bottom are going to cancel out. So I'm not writing them out, because I can factor out the kilograms and they go away. And then throwing this into our calculator, we get negative 0.007796 meters per second square, which, rounding to two decimal places or two singular figures, is 0.0080 meters per second squared. Most importantly, negative, meaning the assumption that the block falls turns out to have been incorrect, and therefore the block actually rises at 0.0080 meters per second squared, and has magnitude here, as we just said, 0.0080 meters per second squared, but the direction is upward. All right, upward. Oops. At 0.0080 meters per second square.